The universe is a tapestry woven from invisible quantum threads. At the heart of modern physics lies a radical idea, the EREPR proposal, which suggests the very stage of reality, the smooth fabric of space and time, is not fundamental. It is an illusion, a magnificent hologram emerging from a deeper layer of quantum entanglement links. By the end of this journey, you will understand how the ghostly connections between particles might literally stitch together the cosmos. We will explore how a wormhole and a pair of entangled particles could be the same thing described in two different languages, and why black holes hold the key to this cosmic code. What does it mean for reality if the distance between stars is written in quantum information? This beautiful illusion of a smooth, continuous universe, however, hides a deep and troubling crack in the foundations of physics. For over a century, two towering pillars have supported our understanding of reality. On one side stands Einstein's masterpiece, general relativity, which describes gravity not as a force, but as the elegant curvature of space and time itself. It paints the cosmos as a dynamic, flexible fabric where planets and stars create dimples that guide the motion of everything around them. This theory is spectacularly successful, predicting everything from the bending of starlight to the existence of black holes. On the other side sits quantum mechanics, the bizarre and counterintuitive rulebook for the subatomic world. It governs particles that can be in two places at once, that are connected by spooky action at a distance through entanglement, and whose very existence is probabilistic, a cloud of possible locations until observed. Quantum mechanics is arguably the most successful scientific theory ever devised, its predictions verified to astonishing precision. Here is the crisis. These two theories, each magnificent in its own domain, are fundamentally, violently incompatible. They speak different languages, obey different rules, and when forced to meet, they produce nonsense. The conflict becomes catastrophic in places of extreme gravity, where the smooth fabric described by Einstein is stretched to its absolute limit. At the heart of a black hole, or at the very first moment of the Big Bang, the equations of general relativity predict a singularity, a point where density becomes infinite, curvature becomes infinite, and the laws of physics as we know them simply cease to exist. It is a mathematical scream of protest, a sign that our description of spacetime as a smooth continuum is breaking down. Quantum mechanics, for its part, abhors such infinities. In the quantum world, everything is granular, everything is quantized, energy comes in little packets. So how can the very stage of reality, space and time, be infinitely divisible and smooth if everything that plays upon that stage is chunky and discrete? This is not a minor technical disagreement. It is a fundamental schism in our understanding of what reality is. Physicists have long known that to resolve this crisis, to truly understand the birth of the universe or the fate of information inside a black hole, we need a new, more fundamental theory. We need a theory of quantum gravity, one that does not treat space and time as a given, but explains where they come from in the first place. The smooth continuum must be an approximation, a large-scale illusion that emerges from something deeper, something more primitive. And that is where our journey into the quantum links truly begins. The search for this deeper theory is the grandest quest in modern physics. It is the hunt for a theory of quantum gravity, a single framework that can finally reconcile the vast cosmic dance of planets and galaxies with the chaotic, probabilistic frenzy of the subatomic world. For decades, physicists have pursued this unified vision along several fascinating paths. One of the most famous is string theory, which proposes that the fundamental constituents of reality are not point-like particles, but unimaginably tiny, vibrating loops of energy. In this view, every particle and every force, including gravity, is a different note played on these microscopic strings. Another compelling approach is loop quantum gravity, which takes Einstein's idea of spacetime as a dynamic fabric very seriously, but suggests this fabric is not smooth. Instead, it is woven from a network of finite, discrete loops, a kind of atomic structure of space itself. These are profound and mathematically beautiful ideas, each offering a different vision of reality's bedrock. Yet from this intense and sprawling quest emerged a proposal so elegant, so conceptually daring, that it reframed the entire problem. This is the EREPR proposal, named for the physicists who conceived it. It did not start by building a new, more complicated set of equations. Instead, it began with a stunningly simple question. What if the smooth geometry of space, the very notion of distance and separation, is not a primary ingredient of the universe but a secondary effect? What if space is not where physics happens but is itself the result of physics happening? The EREPR idea suggests that the true fundamental ingredients are not tiny strings or loops of space, but something even more abstract, the quantum links of entanglement between particles. In this radical picture, the fabric of spacetime is literally stitched together by these ghostly connections. Where there is a strong web of entanglement, there is the familiar, continuous geometry of our world. Where entanglement is absent or breaks down, space itself ceases to exist in any meaningful way. This turns the problem of quantum gravity on its head. Instead of asking how gravity behaves in the quantum realm, we ask how the illusion of gravity and geometry emerges from the quantum realm. It is a shift from building a bridge between two worlds to realizing one world is built from the substance of the other. This profound shift in perspective did not emerge from thin air. It was born from a firestorm of paradox, a cosmic puzzle so deep it threatened to unravel our understanding of reality itself. That puzzle is the black hole information paradox, and to grasp the birth of the EREPR idea, we must first stand at the precipice of one. According to Stephen Hawking's groundbreaking work, black holes are not completely black. They slowly evaporate, radiating away their mass in a faint whisper of particles now known as Hawking radiation. This radiation, however, presents a terrifying problem for quantum mechanics. The theory holds that information, the quantum identity of every particle that falls into a black hole, can never be truly destroyed. Yet Hawking's calculations suggested that as a black hole evaporates and finally vanishes, all that intricate information about what formed it is lost forever, scrambled into meaningless thermal noise. It is the ultimate cosmic shredder. This paradox set the stage for a revolution. In the late 1990s, physicist Juan Maldaisner made a monumental discovery that would light the path forward. He proposed a precise mathematical duality, now called the anti-de Sitter/conformal field theory correspondence, or AD-S/CFT. While the details are intensely complex, the core idea is breathtakingly simple. Maldaisner showed that a theory of gravity operating in a certain warped volume of space is completely equivalent to, and can be perfectly described by, a quantum field theory living only on the lower dimensional boundary of that space. Think of it like a hologram. All the rich, three-dimensional information about gravity and spacetime inside a region is encoded on a two-dimensional surface enclosing it. The universe, in this view, might be a cosmic hologram. This was the first concrete hint that spacetime and gravity could be emergent phenomena, projections from a deeper quantum reality that does not include them. Now enter the ghosts from the past. Decades earlier, in 1935, Albert Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, published a paper aiming to highlight what they saw as a fatal flaw in quantum mechanics. They devised a thought experiment, now called the EPR paradox, involving two particles that become entangled. Once linked, measuring one particle would instantly determine the state of the other, no matter how far apart they were separated. Einstein famously derided this as spooky action at a distance, believing it violated the cosmic speed limit set by his own theory of relativity. He saw it as proof that quantum mechanics was incomplete. History, however, took a different turn. Experiments have since proven that quantum entanglement is real, and it is this very spookiness that physicists would later see not as a bug, but as the fundamental feature of reality. The final conceptual leap came in the 21st century, when physicists like Mark van Romsdonk began to ask a profound question inspired by Maldaisner's hologram. What is the physical substance of the holographic connection? If the interior spacetime is built from information on the boundary, what kind of quantum information creates the geometry we experience? The stunning answer, explored through intricate calculations, was entanglement. Van Romsdonk and others showed that the quantum entanglement between different regions on the boundary is what literally stitches together the fabric of spacetime in the interior. If you were to sever those entanglement links on the boundary, the smooth, connected geometry inside would tear apart, dissolving into disconnected fragments. The EPR paradox of entanglement and the holographic principle of emergent spacetime were fused into a single, radical vision, the EREPR proposal. The spooky action that Einstein rejected might be the very glue that holds his spacetime together. To grasp how entanglement can build reality, we need to understand this ghostly connection on its own terms. Think of it not as a force, but as a shared story. Imagine you have a pair of magical dice, each sealed in a separate, perfectly opaque box. These are no ordinary dice, they are quantum dice. You know that these dice are mysteriously linked. You shake the boxes, you travel with them to opposite sides of the galaxy, and then, at the exact same moment, you open both. One die shows a 3. Instantly, without any signal traveling between them, you know the other die shows a 4. Not because it was forced to, but because their story was written as a pair. Their possible outcomes were always correlated, a single quantum entity split into two locations. This is the essence of entanglement. It is a profound correlation that exists between particles like electrons or photons that have interacted and then been separated. Their properties, like spin or polarization, are not determined individually. Instead, they exist in a shared, fuzzy state of possibilities until one is measured. The act of measurement on one particle doesn't send a message to the other. It simply reveals the already written ending of their shared story. This is what so troubled Einstein, the idea that information about the state of one particle seems to be instantly accessible to its partner, regardless of the immense distance between them. He called it spooky action at a distance, but modern physics accepts this spookiness as a fundamental feature of the quantum world. It is not a signal, it is a deeper form of connection that transcends our classical notions of space and communication. Crucially, entanglement is not just a weird correlation, it is a specific type of quantum information. It represents a resource, a kind of currency in the quantum realm. When two particles are entangled, they share information in a way that is more intimate and interconnected than any classical system could ever achieve. This information is the key. The EREPR proposal makes a breathtaking leap. It suggests that this quantum information, this spooky, non-local connection between distant things, is not just something that happens within space. It is what creates the experience of space itself. The entanglement links are the threads, and the smooth, continuous geometry of the universe is the tapestry they weave. The distance between 2 points, the very notion of here and there, might be a measure of how entangled the quantum information at those locations happens to be. The revolutionary claim of the EREPR proposal is deceptively simple, yet it turns our intuition about reality inside out. It states that the connectivity of space-time, the very fact that 2 points are close together or far apart, is not a fundamental property of the universe. Instead, it is directly related to the amount of quantum entanglement between the underlying quantum degrees of freedom. Think of the universe not as a container, but as a network of relationships. In this view, what we perceive as empty space between stars is not emptiness at all. It is a dense, vibrant web of quantum links, a silent conversation of unimaginable complexity. Where these threads of entanglement are numerous and strong, the fabric of spacetime is smooth and continuous. Points feel close because their quantum information is deeply intertwined. But where there is no entanglement, there is no spacetime connection. It is a stark and profound idea. Two regions of quantum information that are not entangled do not share a geometric relationship. They are, in a very real sense, not even in the same universe from a spatial perspective. They are isolated islands of existence with no bridge of space between them. This reframes distance itself. The vast gulf between Earth and a distant nebula is not a passive void to be crossed. It is an active manifestation of the specific pattern and strength of the entanglement linking all the quantum particles here with all the quantum particles there. The geometry is not the stage, it is the performance, and the script for that performance is written entirely in the language of quantum entanglement. This means that if you could somehow cut or dramatically reduce the entanglement between two regions, the space between them would not just stretch, it would fundamentally dissolve. The smooth continuum would rupture, leaving behind disconnected fragments of reality. It is a concept that challenges everything we think we know about the world, suggesting that the stage of the cosmos is not permanent, but dynamic and fragile, woven moment by moment from the ghostly connections we once called spooky. This idea of spacetime as a tapestry of quantum links finds its most precise mathematical expression in a breathtaking concept known as the holographic principle. It sounds like science fiction, but it is a serious and powerful framework in theoretical physics. The core revelation is this: in certain descriptions of our universe, all the information needed to describe everything happening within a three-dimensional volume of space, including the warping of gravity and the curvature of spacetime itself, can be perfectly encoded on a two-dimensional surface that surrounds that volume. Think of it like a credit card hologram. That shimmering, three-dimensional image of an eagle you see is not actually a miniature bird trapped in the plastic. It is an illusion projected from intricate patterns etched onto the flat, two-dimensional surface of the card. Every bit of depth, every angle of light is contained in that flat code. The holographic principle suggests our universe might operate on a cosmic scale in a similar, though far more profound, way. The world we experience, with its rich three-dimensional depth, the orbits of planets, the swirl of galaxies, and the pull of black holes, could be a magnificent projection. The true, fundamental description of reality might reside on a distant, enveloping boundary, a surface where gravity does not exist and only quantum particles and fields interact according to simpler rules. This means the volume of space containing a star, its planets, and the light traveling between them is not the primary reality, it is the holographic output. The real data, the source code for that entire cosmic scene, is written on the lower dimensional shell that contains it. In this view, you, me, and everything we see are akin to shadows on the wall of a cave, but shadows of such incredible complexity that they believe themselves to be solid and real. The holographic principle provides the crucial stage where the EREPR proposal performs. It tells us where to look for the quantum threads. If the interior spacetime is the hologram, then the quantum information on the boundary surface is the projector. And as physicists probed this connection, they made a monumental discovery. The specific type of quantum information that builds the geometry inside is entanglement. The threads weaving the tapestry are spun from spooky action. From this cosmic hologram emerges one of the most provocative and elegant equations ever conceived, not of mathematics but of meaning. It is captured in a simple, powerful slogan, ER equals EPR. To decode this is to see the merger of two of Einstein's greatest intellectual struggles into a single, unifying idea. The ER on one side stands for Einstein-Rosen, named for Albert Einstein and his colleague Nathan Rosen. In 1935, the same year as the famous paradox, they published another paper exploring the mathematical solutions of general relativity. They discovered that the equations allowed for the possibility of bridges connecting distant regions of spacetime, shortcuts through the cosmic fabric. Today, we call these theoretical structures wormholes. For decades, they remained a curious footnote in physics, the stuff of science fiction, seemingly disconnected from the quantum world. The EPR, on the other side, as we know, is the Einstein-Podolsky-Rosen paradox, the paper that identified the spooky action of quantum entanglement. For most of the 20th century, these two concepts, wormholes and entangled particles, lived in completely separate realms. One was a feature of warped spacetime geometry, the domain of stars and black holes. The other was a feature of quantum weirdness, the domain of particles and probability. They were described in different languages, governed by different rules, and studied by different communities of physicists. The revolutionary proposal ER equals EPR declares that this separation is an illusion. It posits that these are not two different phenomena, but two different descriptions of the same fundamental reality. An Einstein-Rosen bridge and an Einstein-Podolsky-Rosen pair are in essence the same thing. Think of it like seeing a sculpture from two different angles. From one perspective, you describe its shape, its curves, its solid geometry. From another perspective, you describe the play of light and shadow upon its surface. Both are accurate descriptions of the same object. In this cosmic analogy, the geometric description is the wormhole, a literal bridge in the fabric of spacetime. The quantum description is the entangled pair, two particles linked by invisible threads of information. The proposal suggests that every pair of entangled particles is subtly connected by a microscopic wormhole. This is not a wormhole you could travel through. It is fantastically small and unstable, but it is a real geometric connection. The spooky action at a distance is not action through space, it is a connection that is space. The entanglement link is the wormhole, and the wormhole is the entanglement link. This means the ghostly quantum connection that allows two particles to instantly share information has a geometric counterpart, a tiny tunnel stitching together the locations of those particles in the spacetime landscape. It is a staggering unification, suggesting that the quantum information of entanglement and the classical geometry of spacetime are two sides of a single, deeper coin. The universe is not built with space and then filled with quantum particles. It is built from quantum links, and what we perceive as space is the emergent image of those links, with every entangled pair quietly holding open a microscopic door through the heart of reality. But what does this cosmic tapestry actually look like at its most fundamental level? We must abandon the image of a smooth, empty void. Instead, picture a vast and silent ocean of potential, a network of unimaginably tiny quantum units. These are not particles in the traditional sense. Think of them as the ultimate bits of reality, the quantum bits or qubits. In our computers, a classical bit is either a 0 or a 1. A qubit is far stranger. It exists in a superposition, a blend of both 0 and 1 simultaneously, a shimmer of possibility. Now envision a cosmic array of these qubits stretching beyond comprehension. They do not yet exist in space, for space does not yet exist. They simply are connected in an abstract web of potential relationships. This is the raw substrate of reality, a formless network of quantum information. In this primordial state, there is no here or there, no distance, no geometry. There is only the potential for connection. This is where entanglement begins its work. When two of these qubits become entangled, a link is forged. It is not a physical wire or a beam of light. It is a correlation written directly into the quantum code, a shared story between 2 points in the network. Now imagine this process scaling up exponentially. Not just 2 qubits, but trillions upon trillions of them, all becoming entangled in a complex, interwoven pattern. Each new entanglement adds another thread to the growing web. Simple pairs create simple links, But as more qubits join the dance, the links cross-connect, forming triangles, tetrahedrons, and hyper-complex structures in this abstract informational space. The pattern of entanglement becomes a dense, multidimensional mesh, and here is the magic trick of emergence. This intricate mesh of quantum links begins to behave at a large scale, exactly like a smooth, continuous, three-dimensional geometry. The strength and number of entanglement connections between clusters of qubits define their perceived closeness. Where the web is tightly woven, points feel adjacent. Where the threads are fewer and longer, they feel distant. The empty space of a room, the vast gulf between stars, this is not emptiness. It is the visual and physical manifestation of a specific, staggeringly complex pattern of entanglement across the underlying quantum network. The three-dimensional world we move through is the holographic projection of this deeper, interconnected quantum code. We are not looking at the threads themselves, we are seeing the magnificent tapestry they weave, an illusion of continuity so perfect we have built our entire understanding of physics upon it. The true power of this idea lies in its dynamic nature. The pattern of entanglement is not a static blueprint, it is a living, breathing network constantly shifting and evolving. And just as different weaves create different fabrics, different patterns of entanglement create the entire spectrum of spatial geometries we observe in the cosmos. Consider the simplest possible case, a vast, cold, and perfectly empty void. In our everyday experience, this is just flat, featureless space. In the language of quantum links, this emptiness corresponds to a state of maximum uniform entanglement. Imagine that underlying quantum network, with every single qubit connected to every other qubit in a perfectly symmetric, incredibly dense web. The connections are so numerous and so evenly distributed that no single thread stands out. From this perfect, democratic entanglement, the illusion of smooth, flat, and continuous space emerges. There are no hills or valleys in this geometry because the quantum information is shared so completely that every point is, in a sense, equally connected to every other point. This is the calm, silent backdrop of the universe, but our universe is not empty. It is filled with stars, planets, and galaxies, objects that warp the fabric of spacetime, creating the curvature we experience as gravity. How does the entanglement tapestry account for this? The presence of a massive object, like a star, represents a localized disruption in the uniform web. Where there is mass and energy, the pattern of entanglement changes. Think of dropping a heavy weight onto a perfectly stretched elastic net. The net deforms, creating a deep dip. The threads around the weight are pulled taut, while those farther away remain looser. In the quantum network, a massive object is like a knot where entanglement is concentrated and redirected. The quantum degrees of freedom associated with the star become highly entangled with each other, but their connections to the qubits in the surrounding void are altered. This creates a gradient in the entanglement density. Near the star, the web is warped, the connections are reconfigured. This warping in the pattern of quantum links is what we perceive on the large scale as the curvature of spacetime. The star's gravity, the dip in the fabric that guides planets into orbit, is not a force pulling through space. It is the natural geometry that emerges from this specific, distorted pattern of underlying entanglement. An object falls toward the star not because it is being pulled, but because following the geodesic, the straightest possible path through this curved entanglement landscape, leads it there. Even more dramatically, the complete breakdown of spacetime, a black hole singularity, could correspond to a place where the quantum entanglement threads are severed or reconfigured so drastically that the smooth geometric picture completely dissolves. The fabric isn't just curved, it is torn. The tapestry reveals its threads and the illusion of continuous space falls apart. This means that gravity, the most familiar force in the cosmos, might be an entropic force, a side effect of the quantum system seeking the most entangled, most uniform configuration possible. A planet rolling around a star is akin to the network dynamically reweaving itself, smoothing out a kink in the quantum web. So the grand cosmic stage with its flat voids and curved gravity wells is not a fixed set. It is a performance, a real-time projection of an unimaginably complex dance of quantum connections, where every object is both an actor and a pattern in the weave. The profound elegance of this idea would remain just a beautiful metaphor if it were not for hard mathematical evidence. Theoretical physics does not advance on philosophy alone. It demands equations that make precise, testable predictions. And in the case of the EREPR proposal, the clues from the math are startlingly clear. One of the most compelling pieces of evidence comes from a seemingly obscure calculation, the entanglement entropy of a quantum field. To understand this, picture a region of space like a sphere floating in the vacuum. In the quantum field that fills our universe, the particles inside that sphere are entangled with particles outside of it. If you could theoretically cut out that sphere and only look at it, you would lose information about its connections to the outside world. The measure of that lost information, that quantum disconnection, is called entanglement entropy. For decades, physicists calculated this entropy using the complex rules of quantum field theory, expecting a result that reflected the messy quantum details. But they found something astonishing. The entanglement entropy of a region did not scale with its volume, as one might intuitively guess. Instead, it scaled precisely with the area of the boundary surface enclosing that region. This is a bizarre and profound result. In our everyday world, if you want to describe the contents of a box, you think about how much stuff is inside its volume. But quantum entanglement suggests the most important information about what is inside is somehow painted on its outer shell. This area law is a direct mathematical whisper that geometry and quantum information are intimately tied. The entropy, a purely quantum informational quantity, is dictated by a geometric measurement, an area. It is as if the universe itself is hinting that surfaces, not volumes, hold the fundamental data. This whisper became a shout with the discovery of a precise formula, now known as the Ryu-Takenogi formula. Building on the holographic principle, physicists Shinsei Ryu and Tadashi Takenogi found a breathtakingly simple equation. In a holographic universe, they proposed, the entanglement entropy of a region on the boundary is exactly equal to the area of a specific minimal surface that dips into the higher dimensional interior geometry. Let us break that down. On the flat quantum boundary of the hologram, you draw a circle. The entanglement of the quantum degrees of freedom inside that circle is a calculable number. Ryu and Takenogi stated that to find that number, you do not look at the boundary at all. You look into the warped interior spacetime. You find the simplest possible surface, like a soap film, that has the circle as its edge and hangs down into the bulk. Then you measure its area. Their formula declares that these two completely different things are equal, a quantum information measure on one side, a geometric area on the other. This is not an analogy, it is a mathematical identity. The amount of quantum entanglement shared between a region and its surroundings is literally proportional to a geometric object in the emergent spacetime. This formula has been tested and verified in countless theoretical models, and it works with stunning precision. It is the smoking gun in the case for emergent spacetime. It shows that the pattern of entanglement does not just resemble a geometry. It directly generates the very rulers and compasses used to measure that geometry. The fabric is not just woven from the threads determine the length of every stitch. Every calculation using this formula reinforces a radical truth. When we probe the deepest quantum connections of our world, we are not just learning about particles. We are surveying the architecture of space itself. If the entanglement tapestry is real, then black holes are where the threads are pulled to their absolute limit. These cosmic monsters provide the ultimate test lab for the EREPR proposal, the very arena where the idea was forged in the fire of paradox. Remember the crisis, the black hole information paradox. According to Hawking's original work, a black hole evaporates, and the information about what fell in is seemingly lost forever, violating a sacred principle of quantum mechanics. The EREPR framework offers a breathtakingly elegant escape route, one that transforms the paradox into a geometric story. Picture a newly formed black hole. In the language of quantum links, the star that collapsed is a dense knot of entanglement, a highly complex pattern in the quantum network. As the black hole sits in space, it begins the slow process of Hawking radiation, emitting particles from just outside its event horizon. For decades, this radiation was thought to be purely thermal, random noise carrying no information about the black hole's interior. But the EREPR view suggests something far more profound. The Hawking radiation particles are not random strangers. They are born deeply entangled with the quantum degrees of freedom inside the black hole itself. There is a spooky connection linking every bit of radiation to the heart of the monster that emitted it. Now, recall the equation ER equals EPR. An entangled pair is a wormhole. So what does this immense, sprawling entanglement between the black hole interior and the escaping Hawking radiation look like in geometric terms? It looks like a wormhole, a geometric bridge connecting them. This is not a tunnel you could travel through. It is a fantastically subtle connection in the fabric of emergent spacetime, but it is a real geometric link according to the mathematics. As the black hole radiates and shrinks, this wormhole connection does not break. Instead, it evolves. The information about the original star, the quantum data that seemed doomed to be lost inside the singularity, is not trapped. It is slowly and meticulously transferred via this geometric bridge of entanglement into the structure of the Hawking radiation streaming out into the universe. The radiation is not random heat, it is a scrambled but perfect quantum message encoded through the wormhole link. When the black hole finally vanishes in a final puff of radiation, the information is not destroyed. It has all been exported, imprinted onto the radiation field that now fills space. The paradox dissolves. The cosmic shredder has a back door, a quantum tunnel through spacetime itself. This geometric picture suggests that information never actually enters a point of infinite density. It is always connected to the outside via the ghostly threads of entanglement, which are themselves the substance of space. The black hole is not a tomb, but a transformer, converting matter into a holographic message written in Hawking radiation, with every bit of data faithfully preserved across a bridge we once called a paradox. Yet this elegant resolution to one paradox ignited an even fiercer debate, a thought experiment so violent it threatened to burn down the entire peace treaty between quantum mechanics and gravity. This is the firewall paradox, and it asks a terrifyingly simple question. What would actually happen if you jumped into a black hole? For nearly a century, the answer from Einstein's general relativity was clear and strangely serene. The event horizon, the point of no return, would be uneventful. If you were falling into a sufficiently large black hole, you would cross this invisible boundary feeling nothing special at all, a principle physicists call the no-drama postulate. The curvature of spacetime is smooth, and you would glide through without a jolt on your one-way journey toward the crushing fate at the singularity. But the quantum story of entanglement paints a very different and horrifying picture. Remember, for the information paradox to be solved, the Hawking radiation leaking out must be entangled with the interior of the black hole. This is crucial for preserving quantum information, but there is another quantum rule, a strict one called the monogamy of entanglement. In simple terms, a quantum bit can be fully, intimately entangled with only one other partner at a time. It cannot share that deepest connection with two different systems, and here lies the incendiary conflict. As you, the brave astronaut, fall toward the horizon, you are made of particles. Those particles will naturally become entangled with particles just inside the black hole as you cross. But wait, according to the solution to the information paradox, the particles just inside the horizon are already maximally entangled with the old Hawking radiation that left long ago. They are spoken for. The monogamy of entanglement forbids them from being deeply entangled with both the old radiation and your newly arriving particles. Something has to give. In 2012, a group of physicists known as AMPs proposed a shocking resolution. The old entanglement must violently break. The moment you cross the horizon, the quantum links connecting the interior to the early radiation snap. In the quantum world, severing such a vast web of entanglement releases an astronomical amount of energy. The result, the event horizon would not be a peaceful place. It would be transformed into a searing wall of high-energy particles, a literal firewall that would incinerate any astronaut long before they reached the singularity. The no-drama postulate of relativity would be obliterated by quantum fireworks. This was the firewall paradox, a direct and brutal clash between the smooth geometry of Einstein and the rigid rules of quantum entanglement. It seemed you could save quantum information or you could save the peaceful horizon, but not both. The universe appeared to force a cruel choice, yet from the heart of this inferno, the EREPR proposal offers a path to extinguish the flames. The key is in the geometric interpretation of entanglement. ER equals EPR. If the entanglement between the interior and the early Hawking radiation is described as a wormhole, a geometric bridge, then perhaps the rules of monogamy are not what they seem. In this picture, the old radiation and the black hole interior are not two separate systems connected by a fragile quantum thread. They are two ends of the same geometric structure connected by spacetime itself. Your arrival at the horizon does not introduce a new, competing entanglement partner from the outside. Instead, you are entering a region that is already geometrically connected to the outside radiation via the wormhole. You are not forcing an interior particle to choose between two lovers. You are simply stepping into a room that already has a door to the outside. The mathematics suggests that in this geometric description, the entanglement is not violated because the system is fundamentally unified. The wormhole ensures the smooth transfer of information without demanding a violent snap. The horizon remains peaceful because the quantum links are not breaking. They are being reconfigured within a continuous geometric whole. The firewall, in this view, is an artifact of trying to describe a spacetime geometry using only the language of separate, localized quantum particles. When you recognize that the particles are all connected by the deeper architecture of emergent space, the paradox evaporates. So if the EREPR vision is correct, the astronaut's journey remains tragically one way, but at least it is not a sudden plunge into a wall of fire. The event horizon is still a point of no return, but it is a smooth, geometric gateway, not a quantum execution chamber. The drama is in the fate that awaits, not in the crossing itself. The peaceful horizon of a black hole is just one stitch in the cosmic tapestry. To see the full pattern, we must pull back, far back, until entire galaxies are mere specks of light. The EREPR proposal, born from the depths of black holes, now casts its gaze across the totality of existence toward the very beginning of everything. If spacetime is woven from quantum links, then the origin of the universe cannot be a singular point in a pre-existing void. It must be the origin of the weave itself. This leads to a staggering possibility. The Big Bang, that moment of infinite density we have long imagined, might not have been an explosion in space, but the sudden crystallization of space from a state of pure, undifferentiated quantum connection. Think of that primordial quantum network before any geometry emerged. In this vision, the universe did not begin as a tiny, hot dot in an empty expanse. It began as a state of total or near-total entanglement. Every potential quantum bit was linked to every other in a symmetrical, featureless blaze of correlation. There was no here or there, no distance, no time, just a single, unified quantum state. The Big Bang, then, might be reinterpreted as the moment this perfect entanglement began to cool and differentiate. As the universe expanded and cooled, some of those universal quantum links weakened or became more structured. Patterns formed in the web, where entanglement remained strong and uniform, smooth spacetime emerged. Where it varied, the seeds of future galaxies were planted. In this picture, the Big Bang is not a location in space, but a phase transition in the quantum information of reality, the moment the tapestry began to show its distinct threads and colors. This reframes our most fundamental question. We should not ask what happened before the Big Bang in a temporal sense, because time itself is part of the emergent fabric. We should ask what was the nature of the quantum state from which time and space condensed. The answer seems to be a state of supreme, perhaps maximal, entanglement. This perspective also offers a fresh lens on one of cosmology's greatest mysteries, the period of cosmic inflation. For a fleeting fraction of a second after the Big Bang, the universe is thought to have expanded at an exponential, faster-than-light rate, smoothing it out and planting the seeds for all structure. What could possibly drive such a violent, ultra-fast stretching of spacetime? The entanglement tapestry suggests a compelling mechanism. Inflation might not have been driven by a mysterious field of energy, but by a rapid and dramatic rewiring of the universe's quantum entanglement structure. Imagine the early universe as a superheated, hyper-connected quantum network. As it expanded and cooled, the system sought a more stable configuration. This process could have triggered a cascade of changes in how the quantum bits were linked, a great rewiring. And because geometry emerges from entanglement, this massive reconfiguration of the quantum web would have manifested as a breathtaking, exponential expansion of space itself. The universe wasn't just getting bigger, its fundamental informational architecture was rapidly reorganizing, and the spatial geometry we experience was simply keeping pace. The end of inflation, then, would correspond to the quantum network settling into a new, more stable pattern of entanglement, from which the familiar, slower expansion of the cosmos could proceed. The tiny quantum fluctuations frozen into the entanglement pattern during this rewiring would later, through gravity, become the galaxies and the vast cosmic web we observe today. So the largest structures in the cosmos, the great walls and voids spanning hundreds of millions of light years, might be fossilized imprints of quantum entanglement decisions made in the first moments of time. The ghostly links that stitch space together did not just build the stage, they also wrote the script for everything that would ever appear upon it. But for all its breathtaking elegance, the EREPR proposal is not a finished map of reality. It is a compass pointing toward a new kind of destination. Many physicists caution that while the clues are compelling, we are still far from a complete theory. The most significant challenge lies in the gap between a beautiful principle and a working, testable physics. The stunning mathematical results that gave birth to this idea, like the holographic duality and the Ryu-Takenogi formula, were discovered in a very specific, simplified universe. These are toy models, cosmic laboratories with negative curvature, known as anti-de Sitter space. They are beautiful, tractable, and incredibly useful for uncovering deep principles. Our real universe, however, is not like that. Observations tell us we live in a cosmos that is expanding at an accelerating rate, driven by a mysterious dark energy. This gives our universe a positive cosmological constant, a fundamentally different geometric personality, and so far, no one has successfully built a full holographic description for a universe like ours. Translating the EREPR vision from a neat, controlled mathematical sandbox into the messy, accelerating expanse we actually inhabit is perhaps the greatest hurdle. It is like having a perfect theory of ice, only to discover the ocean is made of water. The principles might hold, but the specific machinery must be reinvented. Another profound criticism centers on dynamics. The entanglement tapestry, as often described, seems to paint a static picture. It beautifully explains how a snapshot of space-time geometry could be encoded in a pattern of quantum links. But our universe is not a snapshot, it is a movie. Space expands, black holes form, gravitational waves ripple. How does the tapestry weave itself? How do the threads of entanglement dynamically reconfigure to produce the evolving dynamical gravity described by Einstein's equations? Deriving the full, living dance of general relativity from the quantum entanglement of static qubits remains an open and formidable problem. Some skeptics argue the proposal puts the cart before the horse, using the geometry we want to emerge to define the entanglement we need, rather than deriving the geometry from first principles. Furthermore, the EREPR framework is not yet a standalone theory. It does not replace string theory or loop quantum gravity. Rather, it offers a new language and a set of constraints that those deeper theories might need to satisfy. It tells us what any successful theory of quantum gravity must ultimately explain, that spacetime is an illusion born from entanglement, but it does not yet provide the fundamental microscopic rules for the quantum bits themselves. What are they? Are they strings? Are they loops? Are they something entirely new? The proposal shines a brilliant light on the destination, but the path to get there, the fundamental equations of the quantum substrate, is still shrouded in mystery. These are not minor quibbles, they are the hard, unfinished work of a scientific revolution in progress. The EREPR idea has transformed the conversation, but it has not yet written the final chapter. The unfinished work of a theory does not mean it stands alone. To see the full picture, we must understand where the EREPR proposal lies within the wider landscape of theoretical physics. Its most profound and concrete home is within the mathematical architecture of string theory. This is not a competing idea, but the very framework that gave the holographic principle its precise, calculable form. The connection is forged through a specific and powerful duality known as the anti-de Sitter/conformal field theory correspondence, or AD-SCFT. While the name is a mouthful, the concept is a universe-shaking revelation. It states that a theory of quantum gravity, described by strings moving in a certain warped spacetime called anti-de Sitter space, is completely equivalent to an ordinary quantum field theory living on the lower dimensional boundary of that space. One side has gravity and extra dimensions, the other side has no gravity, just quantum particles interacting on a flat surface. They are two utterly different descriptions of the same reality. This is the concrete mathematical realization of the holographic principle, where the three-dimensional bulk universe is a perfect projection from a two-dimensional boundary. Within this exquisitely precise holographic world, the EREPR proposal transforms from a speculative analogy into a rigorous mathematical statement. String theory provides the dictionary. The quantum field theory on the boundary is a theory of entangled particles. We can calculate the entanglement between different regions with perfect precision. On the other side of the duality, in the gravitational bulk, we have geometries, wormholes, and black holes described by the dynamics of strings. The AD-SCFT correspondence gives us a rulebook for translating between these two languages. And when physicists perform the translation, they find something astonishing. A highly entangled state between two distant regions on the quantum boundary does not correspond to two separate points in the bulk. It corresponds to those 2 points being connected by a geometric bridge, a wormhole. The math forces this interpretation. The entanglement entropy calculated on the boundary using the formulas of quantum information theory is exactly equal to the area of the minimal surface that dips into the bulk, which is essentially the throat of a wormhole. This is not a vague suggestion, it is an equation. In the controlled laboratory of AD-SCFT, the spooky connection of EPR literally builds the geometric bridge of ER. String theory provides the machinery that makes this happen. The vibrating strings and the higher dimensional membranes called branes offer specific mechanisms for how quantum information gets encoded into geometry. For instance, certain entangled pairs of quarks on the boundary can be described as the endpoints of a fundamental string stretching through the bulk. That string is not just a thread of energy in the gravitational picture, it creates a dimple in space-time, a tunnel. The more entangled the boundary particles are, the shorter and more stable that string becomes, pulling the two boundary points closer together in the emergent interior geometry. In this framework, every wormhole, every connection through the bulk, has a direct counterpart in the entanglement pattern of the boundary quantum theory. This gives the EREPR idea a solidity it otherwise lacks. We are no longer just imagining that entanglement might be like a wormhole. In this specific, mathematically defined universe, we can prove they are the same thing seen through two different lenses. The ghostly quantum links are the strings and brains that stitch the cosmos together, and the smooth curvature of spacetime is the large-scale pattern they weave. So while string theory seeks the fundamental ingredients of reality, and the EREPR proposal reveals their emergent pattern, together they form a more complete vision, one where the quantum code does not just run within space, but actively generates the space it needs to exist. String theory's holographic universe is not the only path toward a quantum fabric of reality. Another powerful vision emerges from a radically different starting point, one that takes Einstein's geometric universe at its word, but reimagines its very substance. This is loop quantum gravity, and its picture of space is both beautifully discrete and strangely familiar to our emerging tapestry. While string theory adds extra dimensions and holographic boundaries, loop quantum gravity asks a more direct question: what if space itself has an atomic structure? In this theory, the smooth continuum of geometry is an approximation. Much like a flowing river seems continuous until you see its individual molecules. At the tiniest possible scale, the fabric of spacetime is not a fabric at all, but a dynamic web, a network of finite, vibrating loops. These are not loops in space, they are the loops of space. Each loop carries a tiny, quantized unit of area, a fundamental pixel of geometry. When these loops link together, they form a sprawling, ever-changing structure called a spin network. Picture a vast cosmic mobile with each connection a shimmering thread and each node a bead of pure volume. This mobile is not hanging in space, it is space. The distances and angles we measure in the world are all emergent properties of how this network is connected and how it vibrates. Where the network is dense, space is dense. Where links are long and tenuous, vast cosmic voids emerge. It is a breathtakingly literal vision of a discrete universe. Now, here is where the threads of our story begin to weave together in a fascinating way. In a spin network, the fundamental entities are the links between nodes. Each link represents a quantum of area, a smallest possible patch of surface. For decades, these links were understood purely as geometric objects carrying information about how space is stitched. But a profound question arises: what is the physical nature of this stitching? What is a link beyond a line in a mathematical diagram? This is where the intuition of the EREPR proposal casts a new and compelling light. Could it be that the links in a spin network are not just abstract geometric connectors, but are fundamentally made from quantum entanglement? In this synergistic view, the discrete atoms of space in loop quantum gravity are not isolated pixels. They are nodes in a quantum network, and the links that connect them are the spooky threads of entanglement themselves. The spin network would then be a direct map of the universe's quantum correlations. A region of space with a certain volume would be a cluster of highly entangled quantum degrees of freedom. The area of a boundary around that region would be a measure of the entanglement crossing that surface, exactly as the Ryu-Takenogi formula suggests. This creates a stunning potential bridge between two of the most prominent approaches to quantum gravity. Loop quantum gravity provides a precise, background-independent framework for a granular spacetime built from spin networks. The EREPR insight from string theory and holography provides a potential interpretation for what those networks mean in quantum informational terms. They are entanglement graphs. The geometric links are the entanglement links, It suggests that when loop quantum gravity describes space quantizing into tiny patches, it might also unknowingly be describing the quantization of entanglement. The evolution of the spin network over time, which in loop quantum gravity generates the dynamic curvature of general relativity, could then be seen as the dynamical evolution of entanglement relationships. Space doesn't just exist, it happens through an endless reconfiguration of quantum connections. This synergy is still speculative, a thrilling frontier rather than a settled fact. But it hints at a deeper unity. Whether one starts with strings on a holographic boundary or with loops in a background-free network, both roads may be converging on the same revolutionary destination, a universe where here is defined by how entangled. The fabric is not just pixelated, it is alive with quantum conversation, and every silent link in the spin network might be a whisper of spooky action, literally holding the world together. These profound ideas, born in the abstract realms of string theory and loop quantum gravity, are now stepping out of the chalkboard and into the physical world. The laboratory for testing the fabric of spacetime may not be a particle accelerator, but a quantum computer. Researchers are beginning to use these extraordinary machines not to calculate the universe, but to simulate a small piece of it, to literally build a toy model of reality from the quantum links up. This is not science fiction. In late 2022, a team of scientists made headlines with an experiment on Google's Sycamore quantum processor. They were not solving a logistics problem or cracking a code. They were attempting to create a holographic wormhole. Of course, they did not tear a hole in the fabric of the lab. Instead, they programmed the qubits of the processor to simulate a very simple, stripped-down quantum system that is holographically dual to a spacetime containing a traversable wormhole. They carefully manipulated the entanglement between the qubits, and by reading the output, they could see signatures in the data that corresponded to information traveling from one point to another, as if it had passed through a geometric bridge. It was a simulation, an analogy, but a breathtakingly precise one that tested the core mathematical principles of the ER equals EPR correspondence. The information did not actually travel through a physical tunnel, but the quantum processor behaved exactly as if it had. Think of it like a flight simulator for pilots. The cockpit doesn't leave the ground, but every dial and every response is governed by the real physics of aerodynamics, teaching the pilot how to fly. The quantum computer is a space-time simulator. The qubits and their entanglement patterns are not real space-time, but by manipulating them according to the rules of holography, we can watch how an emergent geometric reality would behave. This opens an entirely new frontier in physics, one of analog quantum simulation. The goal is to program increasingly complex networks of entangled qubits to mimic the quantum systems that might underpin larger and more realistic chunks of spacetime. Can we simulate a tiny, budding universe and watch its geometry expand as we increase the entanglement? Can we create a simulation where we deliberately sever quantum links and observe the corresponding tearing of the emergent space in the data? These experiments are in their infancy, but they represent a paradigm shift. For the first time, we are not just thinking about the universe as a quantum system. We are building small, controllable versions of it to see if the magic trick of emergence actually works. The quantum processor becomes a loom, and we are learning how to weave. The quantum loom forces us to confront a question as old as thought itself: what is real? For centuries, science has operated under a quiet assumption that the stage of space and time is a fixed, objective backdrop against which the drama of particles and forces plays out. This view, known as realism, holds that the universe exists independently of us, its properties definite and waiting to be discovered. But if the EREPR proposal is correct, this bedrock begins to dissolve. How can space and time be objective, fundamental realities if they are themselves contingent, emerging only from specific patterns of quantum entanglement? This is not a minor tweak to our map of the world. It is a challenge to the very idea that the map depicts a territory that exists on its own. It suggests a profound shift toward a kind of physics-based anti-realism, where what we call reality is a useful, stable illusion generated by deeper, non-spatial processes. The solidity of the floor beneath your feet, the vast distance to the moon, the relentless flow of seconds on a clock, all of these would be akin to the convincing imagery of a virtual reality simulation. The simulation is not running in space and time. It is generating the experience of space and time as its primary output. The implications are dizzying. It means that at the most fundamental level, the universe may not contain things that are here or there in any absolute sense. There are only quantum correlations, and from the complex weave of those correlations, the sensation of location and separation spontaneously arises. This leads to a startling possibility that two observers enmeshed in different parts of the quantum web could, in principle, decode the same underlying quantum data into slightly different emergent geometries. There may not be one single true shape of the universe, only a consensus geometry that emerges for creatures like us, who are made of matter and bound by the same quantum rules that stitch the tapestry. The world is not an independent sculpture we are walking around. It is a dance, and we are part of the choreography that creates the stage with every step. Nowhere is this philosophical quake more unsettling than in our understanding of time. We feel time's passage in our bones, the irreversible arrow from past to future. But if space-time is emergent, then time itself must be part of that emergence. In the fundamental quantum network, there may be no universal clock ticking. There may only be a vast web of correlations, a landscape of quantum relationships with no inherent order of before and after. So where does our flowing, directed time come from? A compelling idea is that time emerges from quantum entanglement itself, specifically from the way these correlations spread and become more complex. Think of the universe not as a clock but as a deck of cards being endlessly shuffled. At the beginning, the deck is ordered, all cards sorted by suit and number. This represents a state of low complexity, perhaps even maximal order. As the universe evolves, interactions between particles, the shuffling increase the complexity of their entanglement. The quantum system becomes more and more scrambled, more intertwined in ways that are difficult to unwind. Our psychological and physical experience of time's arrow, the feeling that the future is different from the past, may be our perception of this relentless growth in quantum complexity. The past is a state of simpler correlation. The future is a state of more complex, diffuse entanglement. We are not moving through time, we are witnessing the universe remembering, its quantum connections becoming an ever more intricate story. The now we experience could be a localized phenomenon, a bubble of emergent causality within the timeless quantum whole. This reframes eternity. The universe may not have lasted for 13.8 billion years in a pre-existing time. It may have generated 13.8 billion years worth of quantum correlation complexity, and we experience that accumulation as history. So when you look at the night sky, you are not looking back in time across a static arena. You are witnessing the layered, fossilized structure of the universe's evolving entanglement, a cosmic memory written in light. This vision blurs the line between physics and perception, suggesting that the reality we navigate is not a given, but a shared interpretation of a deeper, stranger symphony of connections. A universe woven from quantum threads is a breathtaking vision, but is it a scientific one? The ultimate judge of any radical idea is not its mathematical elegance or its philosophical appeal, but the cold, hard light of experiment. Can we actually test if space-time is built from entanglement? This challenge strikes at the heart of modern theoretical physics, where the most profound ideas often dwell in realms far beyond our current technological reach. The energy scales required to probe the quantum structure of spacetime directly are unimaginably high. trillions of times beyond what our most powerful particle colliders can achieve. It is like trying to discern the individual atoms in a cathedral wall using only your bare hands. So does this relegate the EREPR proposal to the realm of untestable philosophy? Not necessarily. While we may never take a direct picture of a space-time atom, the universe itself may have already performed the experiments for us, leaving subtle fingerprints in the cosmos we can learn to read. One promising place to look is in the most powerful natural particle accelerators we know of, the violent hearts of active galaxies and supernova. These events produce ultra-high-energy cosmic rays, particles traveling across the universe with energies millions of times greater than those at the Large Hadron Collider. If spacetime has a discrete, granular structure at the Planck scale, these cosmic travelers would feel it. Think of a super-fast speedboat crossing a calm lake. On a perfectly smooth surface, the boat glides effortlessly. But if the water is choppy with tiny ripples, the boat will experience a slight drag, a subtle jitter in its motion. In the same way, a super high-energy cosmic ray flying across billions of light-years would interact with the hypothesized granularity of spacetime. This could cause it to lose energy ever so slightly, or it could affect how the particle interacts with other forms of light, like gamma rays arriving from the same distant explosion. By comparing the arrival times and energies of these different messengers from cataclysmic events, astronomers might one day detect a signature that space is not a perfect continuum, but a seething quantum foam. Another cosmic canvas holds even older secrets, the afterglow of the Big Bang itself, the cosmic microwave background. This faint microwave static is the oldest light in the universe, a snapshot of the cosmos when it was just 380,000 years old. The patterns in this light, the tiny temperature variations that map the seeds of all future galaxies, are exquisitely sensitive to the physics of the very early universe. If the primordial phase of cosmic inflation was indeed a dramatic rewiring of the universe's quantum entanglement network, as some models inspired by emergent spacetime suggest, it could have left a distinctive statistical signature imprinted on these ancient photons. It might appear as subtle anomalies in how the temperature variations are correlated across different angular scales in the sky, a kind of cosmic fingerprint of spacetime's quantum origins. Current telescopes have not found definitive evidence, but next-generation observatories will map this background with unprecedented precision, turning the entire sky into a laboratory for quantum gravity. Within the more controlled mathematical universe of holographic models, the EREPR framework makes concrete, falsifiable predictions. These are tests of the internal logic of the idea. For instance, the mathematics dictates precise relationships between entanglement entropy on a boundary and geometric quantities in the bulk. If a calculation within a holographic model violated the Ryu-Takenogi formula, the entire edifice would crumble. So far, it holds. Furthermore, the proposal makes strong statements about black hole interiors and the fate of information. Any future observation or theoretical breakthrough that definitively proves information is destroyed in a black hole, or that a firewall is real and violent, would deal a severe blow to the geometric picture of entanglement as wormholes. The idea stands or falls on its ability to resolve these paradoxes consistently. So while we cannot yet reach out and touch the quantum threads, the proposal is firmly within the domain of science. It makes claims about how reality must behave, predictions that can, in principle, be proven wrong. The road to a direct test is long and shrouded in the fog of future technology, but along the way, the cosmos offers us clues written in the light of dying stars and the whisper of creation's first breath. The experiment has been running for 13.8 billion years. We are just now learning how to read the data. Behind every radical idea stands a community of thinkers, and the vision of spacetime as a tapestry of quantum links is no different. This is a story of human imagination, of physicists staring into the mathematical abyss and daring to see a pattern where others saw only paradox. one of the most eloquent voices belongs to Mark van Romsdonk. In the early 2010s, Van Romsdonk delivered a series of lectures that would become legendary in the field. He asked a question that cut to the heart of the holographic principle. If the geometry of the interior universe is encoded on the boundary, what happens if we tamper with the quantum information there? His calculations revealed something astonishing. If you take the quantum state on the boundary and deliberately reduce the entanglement between two regions, the corresponding spacetime in the bulk does not just warp, it pulls apart. The smooth geometry fractures into two disconnected pieces. He described this with a powerful analogy. Think of spacetime as a living creature and quantum entanglement as its nervous system. Sever the nerves and the body goes numb, losing its cohesive unity. Van Romsdonk's work provided the most compelling argument, yet that entanglement is not just correlated with geometry. It is the substance that creates connectivity itself. His clear, forceful articulation turned a mathematical curiosity into a central paradigm for a generation of researchers. This paradigm, however, needed a solid stage on which to play, and that stage was built by Juan Maldaisner. In 1997, the Argentine-American physicist unveiled a mathematical masterpiece, the anti-de Sitter/conformal field theory correspondence. While the name is complex, its impact was immediate and profound. Maldaisner discovered a precise, exact duality between two seemingly unrelated worlds, a theory of gravity in a warped space and a quantum field theory without gravity on its boundary. It was not a vague analogy, but a full mathematical dictionary for translating between the languages of geometry and quantum particles. This ad-SCFT correspondence gave the holographic principle rigorous, calculable form. For the first time, physicists could take a question about quantum entanglement on a flat surface, translate it using Maldaisner's dictionary, and get an answer about the shape of a wormhole or the interior of a black hole in a higher dimensional space. His work provided the essential laboratory, a controlled mathematical universe where wild ideas about emergent spacetime could be tested with pencil and paper, and where they kept proving true. Without this foundational discovery, the EREPR proposal would have remained a beautiful speculation, lacking the concrete machinery to make real predictions. If Maldaisner built the stage and Van Romsdonk wrote the script, then Leonard Susskind became its most passionate and public director. A towering figure in theoretical physics and a co-founder of string theory, Susskind has a gift for cutting through complexity with a vivid phrase. He seized upon the connection between wormholes and entanglement and championed it with the powerful slogan, ER equals EPR. He did not just present the equation, he told a story with it, arguing forcefully that the old debate between Einstein and the quantum pioneers was being resolved in the most poetic way possible. Einstein's two great conceptual struggles, the wormhole and the spooky link, were merging into a single description of reality. Susskind used this framework to attack the firewall paradox head-on, arguing that the geometric picture of wormholes naturally preserved both quantum information and a peaceful horizon. His lectures and writings, filled with clarity and conviction, brought these deeply abstract ideas to a much wider audience, framing them not as mere calculations, but as a pivotal chapter in the ongoing quest to understand the universe. Around these central figures, a brilliant constellation of other thinkers added crucial details. Brian Swingle, while a graduate student, showed how the geometry of spacetime could be understood as emerging from a tensor network, a specific kind of quantum circuit that organizes entanglement in a multi-layered web. His work provided a bridge between the abstract principles of holography and the concrete language of quantum information science, suggesting how a universe might literally compute its own geometry. Meanwhile, physicists Shinsei Ryu and Tadashi Takenogi provided what is perhaps the most direct evidence in the math. Their formula, discovered in 2006, gave a precise recipe: the entanglement entropy of a boundary region equals the area of a minimal surface in the bulk. This was the smoking gun, a direct quantitative link between a purely quantum informational measure and a purely geometric one. It turned a philosophical principle into a calculational tool, one that is now used routinely to explore the fabric of spacetime. These architects, each with their own unique insight, did not work in isolation. They built upon one another's discoveries, arguing, refining, and collectively weaving the narrative that our smooth, continuous reality is the grandest emergent phenomenon of all, a holographic mirage sustained by the silent, ceaseless hum of quantum connection. This journey through the quantum tapestry is a story of human curiosity, one where answers often arrived disguised as contradictions. It began with a paper meant to dismantle a theory, not build a universe. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published their famous paradox, aiming to expose what they saw as the absurd incompleteness of quantum mechanics. They highlighted spooky action at a distance, a ghostly connection they believed could not be real. That same year, Einstein and Rosen published another, less famous paper, exploring the strange bridges in spacetime their own gravity equations allowed, structures we now call wormholes. At the time, these two ideas, entanglement and wormholes, were seen as separate curiosities, one a quantum nuisance, the other a geometric oddity. They were the first two pieces of a puzzle, laid on the table with no picture to guide their assembly. For decades, they gathered dust as physics marched in other directions. Then, in the 1970s, a new and shocking piece was forced into the mix. Jacob Bekenstein and Stephen Hawking made a revolutionary discovery about black holes, showing they have temperature and entropy. This meant black holes were not just gravitational pits but thermodynamic objects, and their entropy, a measure of disorder, was proportional not to their volume but to the area of their event horizon. This area law was a bizarre clue. In our everyday world, the entropy of a room depends on how much stuff is in it, its volume. But for the most extreme objects in the cosmos, the information content seemed to be painted on their surface. It was a faint, early whisper of holography, a hint that dimensions could be an illusion. The 1990s brought the clue that changed everything. Juan Maldacén's discovery of the AD-SCFT correspondence provided the mathematical Rosetta Stone. It proved, in a specific and calculable universe, that a theory of gravity in a volume was exactly equivalent to a quantum theory on its boundary. The holographic principle was no longer a speculation, it was a precise duality. Now physicists had a translation guide. They could take a question about quantum entanglement on a flat screen and decode it into an answer about the shape of a wormhole in a higher dimensional bulk. The separate puzzle pieces, the spooky links of EPR and the geometric bridges of ER, were written in two different languages, and Maldacén gave us the dictionary. The final, breathtaking synthesis began in the early 2010s. Mark van Romsdonk asked a simple, profound question using this new dictionary. What happens to spacetime if you cut the quantum entanglement on the boundary? The answer was that the geometry tears apart. Entanglement was not just correlated with connectivity, it was the glue. Around the same time, Leonard Susskind, armed with the tools of holography, forcefully championed the radical equation ER equals EPR. He argued that Einstein's two separate ideas from 1935 were in fact two descriptions of a single, deeper reality. A wormhole is an entanglement link, and an entanglement link is a wormhole. The detective story reached its climax as researchers like Shinsei Ryu and Tadashi Takenogi found the smoking gun formula, directly equating entanglement entropy to geometric area. The clues had all been there, scattered across decades. The spookiness of quantum mechanics, the area law of black holes, the magic of holography, they were not separate mysteries. They were all pointing to the same astonishing conclusion. The smooth, continuous stage of our universe is a magnificent and dynamic illusion, a tapestry constantly being woven by the silent, ceaseless conversation of quantum links. What began as Einstein's stubborn critique had become, almost a century later, the key to unlocking the quantum origin of space and time. The story of the quantum tapestry is far from over, its final chapters still unwritten. So where does this profound vision lead us next? The path forward is paved with both extraordinary promise and deep, unanswered questions, pushing researchers toward a future where the principles we have uncovered must evolve into a complete, breathing theory of reality. The immediate challenge is one of motion. We have a beautiful snapshot, a way to see how a static pattern of entanglement can encode a static geometry. But our universe is not a photograph, it is a film. Stars are born and die, black holes collide, and the cosmos expands. How do the threads of the tapestry weave themselves in real time? The great goal is to derive Einstein's equations of general relativity, with all their dynamic curvature and gravitational waves, not as assumed laws, but as the inevitable consequence of quantum entanglement dynamics. This means discovering the fundamental rulebook for how the quantum network reconfigures itself. One fascinating direction is the concept of quantum gravity. In this class of models, the universe begins in a highly connected, featureless state where every quantum bit is linked to every other. As it cools, the system undergoes a phase transition, much like water freezing into ice. Links in the network break or change strength, and from this spontaneous symmetry breaking, a low-dimensional geometry like our three-dimensional space crystallizes out. The dynamics of this evolving graph could give rise to the laws of gravity and perhaps even the particles of matter themselves. It is a vision where space-time and matter are not separate ingredients, but different vibrational modes of the same underlying quantum graph. Yet, even if we succeed in building such a theory, colossal mysteries remain. We have spoken of space emerging from entanglement, but what of time? Our intuitive, flowing time remains one of the most stubborn puzzles. In the fundamental quantum description, there may be no universal clock. So how does the illusion of a relentless, forward-moving timeline emerge? The leading idea points to complexity. As the quantum system evolves, its entanglement patterns become more intricate, more scrambled. This growth in quantum computational complexity might be what we perceive as the arrow of time. The past is a simpler pattern, the future a more complex one. Our conscious experience of moments passing could be our immersion in this cosmic computation. Then there is the mystery of matter itself. Where do the quarks, electrons, and forces fit into this tapestry of links? Are particles merely knots or twists in the quantum network, excitations that travel along the web like vibrations on a spider's silk? The dream is a theory where a single type of fundamental entity, perhaps a quantum bit with simple interaction rules, gives rise to both the stage and all the actors upon it. The forces, including gravity, would be the statistical tendencies of the network to reconfigure in certain ways. Every open question is a beacon for future research. How does the accelerating expansion of our universe, driven by dark energy, emerge from the quantum links? Can we formulate a holographic description for our real cosmos, not just the simplified toy models? And perhaps most tantalizingly, could there be phases of the universe where the entanglement pattern crystallizes into a geometry with a different number of dimensions, suggesting other cosmic possibilities beyond our own? The journey ahead is not about discarding the EREPR insight, but about building upon it. It must become the foundation for a full, dynamical theory of quantum gravity, one that can make predictions we might one day test in the fading light of distant quasars or in the hum of a quantum simulator. The tapestry is still being woven, and we are just beginning to understand the loom. The universe we perceive is not the primary reality, but a magnificent shadow. After this journey through the quantum tapestry, the takeaway is both simple and staggering. Space and time are not a fundamental stage upon which the drama of particles unfolds. They are the drama itself, a dynamic performance that emerges from a deeper layer of reality, a silent ocean of quantum entanglement links. The smooth fabric of spacetime is a grand illusion, a holographic projection woven moment by moment from the spooky connections that once troubled Einstein. This is the revolutionary heart of the EREPR vision. It reframes our entire cosmic story. Gravity is not a force pulling through space, but a side effect of the quantum network seeking equilibrium. A black hole is not a tomb for information, but a transformer, with its interior connected to the outside by a geometric wormhole made of entanglement. The vast distance between stars is not an empty void, but a living map of quantum correlations. This idea does more than just propose a new mechanism, it heals deep fractures in physics. It offers an elegant escape from the information paradox by showing how data can traverse a wormhole. It cools the firewall debate by suggesting the horizon is peaceful because the entanglement is geometric, not fragile. It unifies concepts that seemed forever separate, binding the quantum weirdness of EPR with the cosmic structure of ER into a single, beautiful equation. We are left with a universe that feels both more alien and more intimate. The solid ground beneath your feet, the expanse of the night sky, the relentless tick of a clock, all of these are emergent phenomena, stable patterns in an unimaginably complex quantum computation. We are not merely inhabitants of space and time, we are participants in their creation, our very atoms part of the weave. The proposal humbles our classical intuition while elevating the power of quantum connection to a cosmic principle. It suggests that at its core, reality is not made of stuff located in places, but of relationships, of information, of conversation. The mystery remains profound, for we still do not know the fundamental rules of the quantum bits or the exact dynamics of the loom. Yet the compass points unmistakably toward a new kind of destination, one where the universe is not a cold, empty container, but a warm, interconnected tapestry, forever being stitched together by the silent, spooky threads of entanglement. This vision of a woven cosmos is not the end of the story, but an invitation to join the conversation. Share your thoughts below. Does this radical idea of an emergent reality resonate with you, or does it feel like a bridge too far? What other aspects of our familiar world might be illusions waiting to be unraveled? For more journeys to the edge of understanding, be sure to subscribe. We explore the deepest mysteries of space, time, and existence, one thread at a time. As we close this chapter, let the final question linger, not as a conclusion but as a doorway. If the universe itself is a vast dynamic web of quantum links, a tapestry of silent conversations, then what are we, as the conscious observers woven into its very fabric, truly made of?